Good afternoon. This is a little video on can I determine the pH of a salt. And you will find that what's labeled AP, and it's generally something that we might do more in AP, but I think you might think or find that possibly not a whole lot new is being introduced here. A couple of small things. Alright, so let's say I have a 0.1 molar solution of NaF. Alright, so first things first, can I determine the pH of the salt? And there also would be maybe a video that I would want to put on here, and maybe I have it on here already, but you should be able to qualitatively determine, is this a weak acid, is it a weak base, or is it neutral? And that's something I do usually leave to the AP level. But either way, today we're going to actually determine what it is. You should note that this is a neutral cation because it is the conjugate of NaOH, which is a strong base, and therefore this is a neutral cation, like I just mentioned. And then this guy is the conjugate of HF, which is a weak acid, and therefore this is a weak base. And with all that being mentioned, my salt of NaF happens to be weakly basic. Okay, now that's the part that I mentioned there will likely be a second tutorial on, or initial tutorial. Okay, so in this case it's weakly basic. Alright, well, what's the actual pH? Well, the Na is doing nothing. It is a spectator floating off. If I were to draw a little beaker of this thing, I would see Na pluses floating around and F negatives. Okay. At this point, my hydrolysis equation is H2O plus, F negative yields HF plus H3. Well, it's basic, so in this case, this guy donates to that guy, leading with OH negative here. Okay, so it's involving a base. I'm going to have a Kb equals concentration of HF, concentration of hydroxide ions, and concentration of HF. And I make sure I got this one right. This one is just the product of, nope. Did have it right. Product is HF. This guy is just F negative. Okay. Fill yourself out a nice table. Now, one thing you're note about this is sometimes they don't give you the Kb directly. For this guy, they're going to give you the Ka of HF. So for this, the Ka of HF is, in this case, 6.6 e to the negative fourth. Now, both HF and F negative are conjugates of each other, so they play off of each other, meaning that they both can't be winners. They both can't be strong. So, as your as your acid gets stronger, your conjugate, let's say X negative, gets weaker, and so on and so forth. So they have a formula for this, which is the Ka times the Kb equals 1.0 e to the negative 14th. Very important formula. It's on your laminated sheet for the AP test. Alright? And if you're given one of them, you can solve for the conjugate of the other half of the test. So the other half of the acid. So it's going to be, in this case, 1.0 e to the negative 14th divided by 6.6 e to the negative fourth, and we get 1.0 e to the negative 14th divided by 6.6 e to the negative fourth, and I get that this guy, the F negative, has a Kb value of 1.5 e to the negative 11th, and this is the Kb value that I would use for this process. That's new as far as this video series is concerned. Alright, so let's go with concentration is going to be 0.1 molar. So this is 0.1, not playing a role, 0, 0, minus x plus x plus x, 0.1 minus x, x. Plug all my equilibrium concentrations into an expression, and I get 1.5 e to the negative 11th equals x squared 0.1 minus x. Utilize the shortcut rule. I get multiply up 1.5 e to the negative 12th, getting smaller, equals x squared. And at this point, I have times 0.1 and then square root that value. I get x equaling 1.23 e to the negative 6th. This represents, in this point, the concentration of hydroxides. Negative log that value, and I get a POH, very important, equaling 5.9. 14 minus that value is, so 14 minus the 5.9 equals 8.09. And that is my pH, which is a basic pH, and you would expect a weak base to be in the basic range. So that is your typical example. Only thing different between this and a regular weak, not much. I mean, I guess you could consider having to use this for any option. Another example where you might use this is typically ammonia NH3 is given on charts. Kb for ammonia is 1.8 e to the negative 5th. Okay, so let's try an example of this guy. Let's say you want to do a concentration of NH4Cl. Alright, you should recognize that this is a weak acid. This is neutral cation, anion. So this guy is going to, let's do a 0.5 molar concentration. So NH4 plus H2O yields NH3 plus H3O plus ion. That's my hydrolysis equation. And then initial stoichiometric ratio end 0.5, not playing a role, minus 0.5, minus x plus x plus x, and then I get 0.5 minus x, x, and x. My Ka value, which I would need to determine yet, is x squared over 0.5 minus x. Likely use our shortcut rule here. Alright, so I need my Ka for this thing. You know, Ka times Kb equals 1.0 e to the negative 14th. I'm given this value at 1.8 e to the negative 5th. Divide out, and the Ka equals 1.0 e to the negative 14th divided by 1.8 e to the negative 5th. And I get 5.5 e to the negative 10th is my Ka value. Plugging that guy into here, and I'll do the math quick because we have been doing this a bunch of times here. I'm going to multiply times 0.5 square root times 0.5 square root that particular answer, and I get the x value 1.6 e to the negative 5th moles per liter. That equals the concentration of H2 plus ions. The negative log of that gives me my pH. And we get 4.7. So another example of some of these weak acids, weak bases. Now again, we call it salt because only because I'm providing for you the entire salt to begin with, which is the cation and the anion. And you just split it up and give it a try. Thank you very much.